Good evening. This lesson is the second lesson in the nuclear physics module. We will be covering half-life and talking about some different ways that this can affect the radioactive particles, and also do one practice problem. We also will talk about a half-life graph as well, which could help with your lab. So for any given radioactive atom, and the decay process is purely random, it is impossible to predict when a single atom will decay. However, based on probability, we can approximate the number of nuclei in a sample that will decay, and if the sample is large enough to get a very accurate value. The more particles there are, the more it would be expected to decay. Next, we're going to be talking about the decay constant. The make and probability and to inequality, we add a constant. The value of that constant is determined by the specific radioactive isotope. This is supposed to look like this. Not sure why that's not showing up. It's called the decay constant. So every time you see this symbol in a formula, that is going to be the decay constant. The rate of decay is the number of atoms that undergo decay in a specific period of time is called the decay rate. The number when half the number of particles have decayed is considered the half-life. The greater the decay constant, the greater the rate of decay, or the more radioactive the particle is. The half-life of a radioactive isotope is the time it takes for half of the original of the parent isotope to decay. So that's T1/2. So we know that carbon-14 has a half-life of 5,730 years. What is the decay constant? So first we have to convert years to the standard time unit of seconds. This is really important, and most students forget to do this step. So we have to convert how many seconds are in that 5,730 years. So this formula right here is the conversion formula. So it would be 1.81 times 10 to the 11th seconds. The unit for the decay constant is 1 divided by second. So also you can see it as 1 over S. Or like you see down here, that's the unit. So now you plug it into the relationship. So T1/2 equals 0.693 divided by the decay constant, which becomes the following. So the decay constant we calculated in seconds up here, which is the half-life. So 0.693 divided by 1.81 times 10 to the 11th, and we should get 3.83 times 10 to the negative 12. The becquerel is 1 decay per second. So what is the decay rate of carbon if there are 1.00 times 10 to the 22nd atoms? So what we're going to do is we'll use this formula that you see here. Change in the number times the change in the time equals the decay constant. So we plug in what we know, 3.83 times 10 to the negative 12 times 1.00 times 10 to the 22nd, because that is this number right here. And we should get 3.83 times 10 to the 10th becquerels, which stands for BQ. For specific multiples of half-lives, we can determine the number of parent and daughter nuclei. After one half-life, half the parent nuclei have decayed to daughter nuclei. For the next half-life, the half-parents left have half of them decay again, so only 1/4 of the parents remain, and 3/4 are now daughter nuclei. After third half-life, the parents only 1/8 of the parents remain, and now 7/8 are daughters. So in other words, it's going to be half the number that's left turn into daughter nuclei. So to represent in this graph, you see it below. So this is hopefully what your graph looks like for your lab. If you haven't done it already, this is a good way. This is the pattern you should see if you're doing it correctly. So what we can do is pick out a point on the graph and then calculate the half number. The time period between these 2 points is the half-life. So looking at the graph of the decay of substance, you can determine the half-life by the time it takes to decay half of any amount. Every hour, the total amount of parents is reduced to half the previous value, so half-life is 1 hour for this specific example below. So in other words, we'll talk about it on the graph. So right here we have 50%. So half of 50 would be 25, so the point that it reaches 25. So the time difference between this point and this point in this scenario is 1 hour. Now here is the practice problem for this lesson. Okay, so we're going to use this graph of decay of oxygen 14. Determine the half-life of oxygen 14. So what we're going to do is pick any point and a second point, which is half of much mass. So let's just go ahead and do the top, which will say 300, and then we need to see where it hits 150. And this is what we're going to calculate for the half-life. So, for example, at T50, there is about 180 grams. So the example problem would be right here. Might be easier to use. 90 is about T equals 120. So what we're looking at here is half of 180 is 90. So around 90, you're going to be right about here. And that's going to be close to 120. So the half-life should be about 70 seconds. Because that's going to be the difference between 120, oops, that's not a straight line. So we're looking at here, which should be the same if we did it 300 to 152. So if the decay constant for oxygen 14 is this number, 0.009816 1/seconds, calculate the half-life of oxygen. So all we do is use 0.693 divided by the number that's given to us in the problem, and we should get 70.6 seconds. And does that check out? Because we estimated up here and both of them are close to 70 seconds. So now we have 292 grams of oxygen 14 is 1.26 times 10 to the 25th atoms. What is the initial decay rate for this sample? So what we're going to use is this formula down here and plug in the decay rate, which was given to us in this part of the problem, and then plug in how many atoms, the number of atoms, which is that change in N, 1.26 times 10 to the 25th, and we should get 1.24 times 10 to the 23rd becquerels. The next part says how many grams are left after 6 half-lives. So what we're going to have to do is take half all the way down to 6 half-lives. So we started with 292. Again, this is coming from this part of the problem. Divide that by 2. Get 146, so that is the first half-life. 146, half of 146 is 73, 2. 73 divided by 2 is 36.5, and you're going to continue to divide by 2 whatever is remaining all the way. So after 6 half-lives, you should only have 4.56 grams left of oxygen 14. The last part of the problem says how many grams are left after 212 seconds. So you have to think about how many half-lives there are. So we have 212 divided by 70.6, which is, we know, the time it takes. So we got 3. So what we're going to do is go down for 3 half-lives. So 192 divided by 2 equals 146. 146 divided by 2 is 73. 73 divided by 2, and we should get 36.5 grams. And that is it for the practice problem and the second lesson over half-lives. Please let me know if you have any questions.